Remember, geometrically, when we define the real numbers to be those numbers whose squares are non-negatives, we do not need any picture to visualize that. It just happens that the number line, the x-axis, is a very convenient way of visualizing real numbers pictorially. What we're saying is that since complex numbers seem to indicate a two-dimensional vector space, namely real and imaginary parts, which are independent, it would appear that the analog for visualizing complex numbers pictorially would be to use the plane. And that's exactly what we do. The diagram is called the Argand diagram. The idea is this: given the complex number x plus iy, which we'll call z, we visualize z as either the point x comma y in the xy plane. In other words, notice that the x-axis is the real axis, meaning it denotes the real part of the complex number. The y-axis is called the imaginary axis because it denotes the coefficient of I, the imaginary part. Okay? And what we're saying is we can visualize the complex number x plus iy to be the point x comma y, or for that matter, the vector that goes from the origin to the point z, whose components are x and y, meaning what? X plus iy. The components are the real and the imaginary parts here. We can translate this into polar coordinates, meaning that we can measure the point z by its r value and its theta value. But one important thing to remember is that in polar coordinates, it's always assumed that r is positive. Unlike the usual polar coordinates where r could be either positive or negative, the idea is that we would like to identify the absolute value of a complex number with being its distance from the origin. Since we want absolute value to be non-negative, we simply say that r is the positive square root of x squared plus y squared, and that names the magnitude of the complex number. The angle theta is called the argument, abbreviated ARG, not to be confused with this funny coincidence of Argand diagram. This comes from the word argument, argument. The angle is called the argument, all right? And if you elect to write the complex number x plus iy as r comma theta, because of the connection between polar and Cartesian coordinates, see, x is what? X is r cosine theta, y is r sine theta, so the complex number is r cosine theta plus I r sine theta. That's what r comma theta denotes. Now, using this as background, so we now have what? We've invented, at least abstractly, a system of numbers called the complex numbers. And by the way, let me point out here that don't use the word imaginary too strongly. There is certainly nothing imaginary about this geometric interpretation. What may be imaginary is I may not have a place where I want to use these kind of numbers, but believe me, we wouldn't have made a whole block of material about these numbers if there weren't real interpretations of the so-called complex numbers. This is a perfectly real geometric interpretation. So far, we have established the fact that this interpretation gives us a vector space